We're happy to have Yidi Qi here telling us how to construct Calabi-Yau metrics numerically. So take it away, Yidi.
Yeah. So it's the first time I've ever given a talk to an audience over 30 people. So thanks so much. And my name is Yidi Qi. I'm currently a grad student at Stony Brook University. And this talk is basically based on our paper in December, together with Professor Michael Douglas and my colleague Nam. So today I'm going to talk about the numerical Calabi-Yau matrix from the holomorphic networks. So as many of you have already known, the Calabi-Yau manifolds, they were proven to admit Ricci flat matrix, and they actually they play an important role in the string phenol and have many important applications, such as the computation of the Yukawa couplings. And however, it's generally believed that there's no closed form expressions for the compact Calabi-Yau manifold. Therefore, it's kind of important to get the numerical approximations. And there have been a fair amount of work on this, and it's basically starts from Donaldson's method, and then it's further developed by DKLR's paper, and also some other very interesting papers, such as the ones by Hendricks and Nassar. And so I think many of you have already familiar with this, but let me just briefly reveal the idea, what we call the embedding method. So one simple example, for example, as in the Calabi-Yau manifold, is the quintic hypersurface in CP4, and then we can pull back the Fubini-Sadi matrix, which is defined by the Calabi potential, and then get a family of the matrix. And in this way, we can have this H is a positive definite Hermitian matrix, and then we have a parameter space of approximately 25 parameters. And to generalize this, we can replace the coordinate z with a basis of section of a line bundle. So this is basically just the homogeneous polynomials of degree k. And in this way, we can have a much higher parameter space when we increase the parameter k, so that we can have a larger H matrix. And the geometry of a Calabi-Yau manifold is determined by the two fundamental differential forms. The first one is what we call the Kähler form. It exists on every Kähler manifold. It's defined as omega equal to delta bar k, where k is the Kähler potential. And then we can use the Kähler form to write the corresponding volume form, d mu g, and then which is just the determinant of the delta bar k. And another important differential forms is the non-managing holomorphic n form, and this only exists on the Calabi-Yau manifold. And we basically note this as omega, and we can write down the holomorphic volume form by d mu omega, which is equal to omega bar. And for Ricci flat matrix, we know that those two volume forms should be equal if we choose appropriate normalizations. And in other words, we can define the ratio eta as the d mu g over d mu omega, and this value can be set to 1 by choosing the normalization. Okay, so now with this embedding method proposed by Hendricks and Nassar, we can minimize an energy function, which is defined as the integration over the integration of eta minus 1 squared over the whole manifold, and eta is the ratio of the two volume form we just defined. So by minimizing this energy function, we can get a good approximation of the Calabi-Yau matrix, and then we can show that this approximation error will decrease when we increase the the degree k of the polynomials. However, although this works, but the number of parameters will actually also increase in the order of k to the power of 6. And it demands a lot of computational resource, especially when we have a k equal to over 14 or 15. And that becomes very hard to calculate. So most of the previous work, they only consider the symmetric hypersurface so that you can use the symmetry to reduce the number of parameters you have in H. Okay, so that's the basic idea of this embedding method. So I think many of you have known the geometry, but maybe some of you may not be familiar with the machine learning problem. So then let me talk about what is a typical supervised learning problem looks like, and we can compare the similarity between the problem of Calabi-Yau matrix with the machine learning problem. So there are actually many powerful algorithms in machine learning, and the one of the most popular and also one of the most successful model in recent years is this we call this neural network, and it's also actually a feed-forward network. It's a multi-layer network structure. So basically, we have an input vector, and then you multiply this input vector by some weight matrix W, and then you go through some nonlinear activation function theta. So the reason we have this nonlinear function is because if you only have the linear transformation in each layer, the total number of linear equations you have will not increase even if you increase the number of parameters. So we just make them nonlinear to have more equations. And then you basically just multiply the input by the first layer and go through activation functions, and then you just go through the next layer and so on and so on. At the end, you have some kind of output layer, and it's basically just a map from your input points to your output. So so it can be shown that this kind of map, this kind of a function, can approximate any sort of functions you have. So that's why it's very useful in all kinds of problems. This is what we call the universal approximation theorem. And now the question is, how do you find the correct relation you want for some specific questions? And we introduce this thing called loss function. It's basically a measurement of your performance of your network. So here are two simple examples. The first one is what we call the mean square error, the MSE. It's basically the square, the average of the square of your prediction of network minus the y, which is the true value of the output, or sometimes we call it as a label. So you measure the differences from your prediction to the true value, and then you take the average. And a similar example is the mean absolute percent error, which is called MAPE. It's basically the same thing, and you can choose all different kinds of loss function for your questions, and they may have a different performance. So once you have this loss function, you can find some appropriate training methods so that you can update your parameters in the network so that you can have you can get the correct relation you want. So one simple algorithm is the gradient descent. It's basically supposed to have this large parameter space of the weights, and you start from some random points. You just go along the direction of the gradient until you reach the minimum. So this is the simplest example, and actually later we can see that this actually doesn't work in all network settings. But in general, you have some sort of data set, and you use a network to construct this function, this kind of mapping, and then you use the loss function to measure your performance, and you use some algorithm to train your network to get the optimized function you want. So now let's compare this to the Calabi-Yau matrix problem. So we have the input, which are the Monte Carlo points on the hypersurface, and we can also calculate some label y, which is the holomorphic volume form, because we know they can be explicit calculated on a hypersurface without any network structures. And once we have the data set, we already have the loss function, which was proposed. The one I just showed you, proposed by Heydrich, is the integration of eta minus 1 squared over the manifold, and eta is the ratio of the two volume form. So now the question is, how can we construct our function f, and how do we find the appropriate training algorithm to train our network? So there are actually many ways you can do this. You can map the points on the surface to the color potential. You can map the points to the the elements of the matrix itself, and also there are many different ways to construct networks. So there are actually a bunch of ways to do that. But here we try to keep the mathematical form of the color matrix and the color potential as much as possible. And also we want to make it homogeneous. So there are actually two ways we propose in the paper. The first one is what we call the holomorphic network. It's basically you have this color potential in the embedding method. You replace the homogeneous polynomials HSS here by some complex networks. So you have F here is this all of the weight matrix here are complex numbers, and then you take the coordinates of the points as input and multiply that by the weight matrix, and then you go through a theta function, which is just a square function. And so basically your input will be squared after each layers, and then the output of this network will be a vector of the sections with the degree k equal to 2 to the power of d, where d is the number of layers you have. So if you have a 3-layer networks, then you're going to have then it's equivalent to a k equal to 8 settings in the embedding methods. And once you have that, once you have the output of your network, you can multiply that by the complex conjugate, and then your color potential is going to be like this. And so this actually doesn't work too well for many reasons. So first is a complex network, which is not the usual choice in the most of the machine learning problem, because in real world most of them are just real number problems. And also you have to multiply the output by the complex conjugate, which makes the networks much more complicated. So it turns out the performance of this setting is not too good. So then we propose another kind of network, which is called the bihomogeneous networks. It's mostly the same thing, but then we take the input, we take the real and imaginary parts of the combination ZZ bar as input. So instead of the complex input, we now have all real inputs, and then all of the weight matrix will all be real as well. And the theta activation function is also the z square. So everything else is the same. So but here we have only a single output, because in the end it's just a summation of all of the polynomials, and then we take the log to make the color potential. So this actually works pretty well in the later experiments, and this is what we're going to use for the future experiments. So now let's look at the training algorithm. It turns out the traditional gradient descent doesn't work, because one reason is because the activation function we use, the z-square function, is actually not a popular choice in the machine learning problem, because in these configurations, the weights in the front layer will have a higher degrees than the weights in the rest of the layers. And in this case, especially when you calculate the gradient, it's very easy for them to either blow up or either vanish during the whole optimization process. And to solve this, we actually used a two-phase training method. So the thing is we use is called the Adam algorithm. We will not have time to give more details on this, but it will keep an individual learning rate for each parameters, so that the training process can be smooth. And then after you reach the region near the minimum, the Adam algorithm is actually pretty slow. So we used a Newton method, it's called LBFGS, to do the optimization. And okay, so now let's go back to the Calabi-Yau matrix problem. We have the dataset. we replace the input from the points to the combination of the z bar, and we still use the holomorphic volume form as the output. And now for the function, we have this network which maps those inputs to the Calabi potential, and then we calculate the volume form from the Calabi potential. And then we have still use the same loss function, the integration of eta minus 1 squared, and we use the 2 training algorithm. Okay, so now we can use the whole machine learning language to describe this geometry problem. So now the question is, why do we want to do this? Why do we want to use machine learning to describe this? There are many reasons. First is that it's very interesting, and also it has many practical reasons we want to do this, because this kind of structure is actually very popular, and we have a lot of hardware and software specially designed for this kind of questions, for the also for the tensor operations, and also the auto-diff techniques used in the TensorFlow, and also in some other training algorithm. They're actually very fast, so you can speed up the whole training process, especially when you're taking try to optimize the weight matrix. And so basically, with all of those well-developed package in the industry, we can actually get really high accuracy with a really fast speed. Okay, so our implementations, we have our code on GitHub, and although most of the functions is actually already inside the TensorFlow packages, we still need to write some special code for the mathematical tool we need in these questions. So we packed all of those in the package we call the ML geometry, and as you can see here, we can describe a network using the software in a very neat way. So you first have this bihomogeneous layer, which takes the 5 input coordinates to approximate 25 ZZ bar, and then you can followed by the multiple layers you want with the TF square activation functions, and then at the end you have a lot of functions which reproduce the Calabi potential. Okay, so with our package, we did a lot of experiments. We basically scanned through the Calabi-Yau manifold with different symmetries. So the first one we checked is the one with the full symmetries, just the one I just showed at the beginning, and also the f equal to f1 with this parameter equal to 0. And then we have the 2-parameter family with the less symmetries, and also another 2-parameter family with with no symmetries with this large terms here. Okay, so those are the 3 examples we use in the experiment, and this is like a simple training process. And the y-axis is the log of the training error, and x-axis is the number of training epochs. So as you can see, it's basically reached some kind of minimum after a few training epochs. Okay, and there are two kinds of parameters we want to study, and the first one is the geometry of the Calabi-Yau. So one is the symmetries I just showed, and also the other one is the distance of the hypersurface to a singular hypersurface, and the distance is defined as using this proxy. And also we have the parameters in network, including the depths of the network, and also the total number of parameters. And we scan over all of those parameters and try to find some dependence of the accuracy. And here's a plot of the distance with singular Calabi-Yau for the quintics, and the x is the parameters and the y is the distance. You can see there's like a local minimum around 5, and then you have a minimum around -5. And these are 2 plots for also for the distance over the parameters in f1 and f2. Okay, so and this is our part of our results for f1, and x is the distance to a singular Calabi-Yau, and y is the training error. So you can see the points with different colors, they represent different kind of network structures. So this one here, 5051, is basically a 2-layer network, which corresponding to k to 4, and you have a total number of parameters, which is 50 times 50 plus 50 times 1, and also we actually have a bihomogeneous layers in the front, so we have another extra 25 times 50. And then this purple points are for a 3-layer network, which is corresponding to k to 8, with the network width 70, 70, and 70. And then you have another same 3-layer networks, but you have more parameters here. And you can actually see that this pink point here is the estimation using the traditional dominance embedding method. So you can see that actually, if you increase the number of depths in networks, it's like moving k from a small k to a higher k. And then in this case, it's actually you have a much better accuracy. And this one is for f1. I think you can clearly see this differences from 50 to the 70 here. And also, even though you have the same k, like the purple points and the green points here, they have the same k, but then they have a different number of total parameters, and that will also affect your accuracy. Okay, so in summary, we developed the Tensorflow Keras package to approximate the numerical Calabi-Yau matrix, and also we can use this model to many other interesting geometry questions. And also, this kind of network has many interesting questions in machine learning as well, but we will not have time to give more details in this. And also, there has been a lot of interesting papers in these topics using machine learning, and those two are actually very recent. In the same month, we published we put a paper on ORCID. So I think this is a very this kind of it's a very interesting field, and there's a lot of potential in the applications of machine learning in this Calabi-Yau matrix problem, and also in string theory and high energy theory in general. And I will stop here. Thanks so much, and let me know if you have any questions.
Great, Yidi. Thanks for the very nice talk. While we wait for questions, I have one. Oh, sorry. Before we move on, let us thank Yidi with our clap emojis. Yeah, I was wondering, so this loss function that you had, it's how good is it at measuring zero Ricci curvature? Like if I minimize this, if I get this loss function to 10 to the minus 5, can I be sure that the Ricci curvature is no bigger than 10 to the minus 4 or something, or in some integrated sense? Like, is there a worry that minimizing this, getting this loss function to be small but non-zero doesn't necessarily result in very small Ricci curvature?
Yeah, that's a good question. I think in the original paper of Hedrick and Nassar, they actually discussed about that, and then I think they actually show that you can actually have a small Ricci curvature if you minimize this empty function.
I see. And this activation function, the z squared, once you went to the non-holomorphic network, usually these activation functions are a lot more nonlinear. Do you get a lot of benefit from going to different, like a sigmoidal activation function, or?
Yeah, so basically, yeah. So basically, the reason we want to choose the square function is first we we can keep the mathematical structure, but also want to make sure it's homogeneous. Like when we rescale the coordinates, we want to make sure it's homogeneous. So that's why we use this square. But also you can also use some other homogeneous functions. That will be also another very interesting topic, but we have not. Yeah.
Well, if there are no other questions, let us thank Yidi again for his very nice talk.